Good morning, everyone. Are you able to hear me? Wonderful. Hello, everybody. Sorry about the mess up a few minutes ago. Technology tried to fool us. My name is Michael, not Matthew, although shown on the screen, it's just the scheduled host for this session had to attend a board meeting and is not able to come, so I took over his position. I'm from the Melbourne Center for Nanofabrication, and I wish you all a warm welcome to the webinar series of the third Direct Write Lithography workshop. Before we start with the webinar, I'd like to say a few words and acknowledge a few people. First, I'd like to recognize the traditional owners of the land. In my case, that's the people of the Kulin Nations on whose land we are gathered today, and I pay my respects to their elders, past and present. I'd also like to extend my respects to all Aboriginal and Torres Strait Islander peoples. Next, I'd like to thank the Australian National Fabrication Facility, ANFF, which is our head organization, and ANFF provided a lot of funds and resources to make this workshop happen. Especially, I'd like to thank our CEO, Jane Fitzpatrick. If you're interested, I'd like to know more about ANFF. This is the website. Then, finally, I'd like to thank the whole team who put in a lot of effort in organizing the workshop. If you'd like to know more about us, this is our website, which also conveniently sits within ANFF, so you can just move around between ANFF and the workshop itself, or the workshop committee. Some faces you might be familiar of, especially when you are zooming in from the US. For example, this year I had a chance to visit the 3Beams meeting in San Diego, or EIPBN. Elliot, that's him here, he was invited to attend the Mabel meeting in Atlanta, so meeting for advanced electron beam lithography at Georgia Tech. And both of those conferences highly influenced us to set up this workshop, and we're very thankful for the help of James Owen, who is the conference chair for the 2025 EIPBN meeting, and of course especially thankful to Gerald Lopez, who is a co-founder of Mabel and was I think in 2021 the conference chair of EIPBN, for the help and their support in advertising this event, especially in the US. All right, before we start the webinar, I thought, or we thought we're going to share some attendee statistics. So we have roughly 25% of overseas attendees. We have around about 100, a bit more than 100 people signed up, which is very nice. We're very, very happy about this result. From the Australian attendees, the biggest block is from Melbourne. But let me say this, it's not a competition. So there's room to ramp up numbers. All right, then let me move forward. For the reason we're all gathered together today, the first webinar, a few words about the webinar, took some notes. So firstly, the webinar will be recorded, and we will share the video with everyone who signed up. But we only do that after the workshop in February. So 19th of February is the actual workshop, and afterwards we make all the videos where the presenters allowed us to share the video. We will share those with you. Christopher will only join us for the second part of the webinar due to other commitments, but he kindly shared with us a video, which we just got to run in the last minute before the webinar actually started. So we had sound issues. There's always something, I guess. As soon as the video is finished, which takes around about an hour, I'll formally introduce Christopher, and then he suggested to start with a Q&A about the video we all just watched. So if you have questions, either raise your hands or put them in the chat, and we go through them together with Christopher. Once the Q&A is done, he will continue with the second part of his webinar, and then we have another Q&A session, and yeah, we should be all done in 2 hours. All right, that's it from me. I'll be back in 1 hour. Let me stop sharing this screen and start sharing this screen here. Okay. Please let me know if you don't hear the sound. And here we go.
Well, good morning. It's a pleasure to be here. My name is Chris Ober. I'm a professor of material science and engineering at Cornell University. And one of my research areas is in advanced lithography. So I really want to thank Michael for the chance to talk at the third DWL workshop. And what I'd like to do in this recorded part of my presentation is talk somewhat about the history of lithographic resists. In the first part, I'm going to talk about systems generally that have been implemented. And in the second part, I want to talk a little bit about the future. So although it's the history of resists, I'm going to predict the future somewhat. Okay. So what I'm going to do is talk about really a living history. So even as we have systems that work quite well, advances in electronics, advances in understanding, really help us continue to evolve the whole range of technology. Today, the semiconductor roadmap asks for really demands sub-10 nanometer patterning. We hear about advances in all types of semiconductor chips. We hear about advances in nanolithography for applications outside of microelectronics. And today it's still a challenge, but it's rather routine to be able to produce these tiny structures. As an academic, the most easily accessible tools are going to be advanced e-beam patterning tools. At Cornell University, where I teach, we have state-of-the-art Joule 9500 that in which, in a hero experiment, we can produce perhaps 6 nanometer lines and spaces. So new semiconductor architectures are demanding these types of structures. New approaches are being developed. Old strategies are being revisited. So I'm going to talk about in the second lecture about materials and systems that were developed decades ago, but are also being brought out of mothballs because they may be the perfect systems for the next steps of patterning. And another important aspect is that we understand everything better than just a few years ago. And so we can use the same materials and do a much better job. This whole area of PFAS that's come up, the concern about fluorinated chemicals, forever chemicals in the environment, is something that's going to affect availability of patterning materials going forward. But I've elected, as important as it is, not to address that because in some ways, in the case of chemically amplified resists, most of the PFAS problem is not from the patterning itself, it's from other aspects of the semiconductor manufacturing process. And so from the patterning perspective, I think we're good. Also, as an academic, I have to thank all the organizations that have supported the work that I've done, some of which I'll talk about in lecture 2. And that includes JSR, Intel, the Semiconductor Research Corporation, and some of the folks that I've collaborated with, and some of the folks that I have depended on in my research group. Okay, so for patterning, we really depend on the fact that Moore's law has driven development of technology, tools, and materials over the last few decades that enables us to get to these very small dimensions. Without the semiconductor industry, there really wouldn't be the motivation or the financial wherewithal to build these types of capabilities. And I really also like to look at this plot, which increasingly is hard to find. This is from the Intel website a few years ago, and it only shows from 1970 to 2000 a version of Moore's plot in terms of the number of transistors on a device. On the left-hand side, what you see are basically 3 data points from early chip devices that Intel was building. And from those 3 data points, a line was extended in the future, and it really has been pretty remarkably consistent. So I got concerned about Moore's law as a new professor and had to buy a computer in order to function. And in those days, the feature sizes of half a micron and processors with thousands of transistors operating a few megahertz were the norm. Yeah, we could still do stuff in those days, but the screens tended to be black and white, and that's largely the major difference between what we work on today from a user experience. But very rapidly, we went to hundreds of millions to billions of transistors in a single device. And we had devices that work at the gigahertz regime, feature sizes of 100 nanometers and less. And now we're just talking about a few nanometers. So what Moore's law represents to me is actually a plot of how rapidly technology can advance and how with continuous improvements we can push a technology forward. So the ITRS roadmap described how it really plotted out how progress should occur. This is an interesting historical document. In many ways, it's no longer relevant, but if you can look at the slide, you'll see some important mileposts. At the time this was drawn up, 248 nanometer lithography, use of ultraviolet light at 248 nanometers was a big chunk of the more typical chips. The 193 nanometer lithography was coming in, and as we go down, we see a blue box, the lowermost blue box, showing 157 nanometer lithography, which came and went around the year 2000. We see EUV lithography that was supposed to kick in around, well, between 2010 and 2013. And it was delayed a little bit, but it did show up. We see EUV lithography competing with electron projection lithography, and EPL has never really materialized. And now we are looking at what they said was innovative technology, which was going to step in and save the day, but it turns out it's EUV. And so there have been intellectual battles over which technology should come first, which one will move forward. But whether it's going to be massively parallel E-beam lithography or EUV lithography, but in the end, for semiconductor processing, the EUV, extreme ultraviolet light, 13 nanometer radiation, has won the battle for the next while. So now, in 1959, Richard Feynman talked about there being plenty of room at the bottom. Integrated circuits were certainly in the offing. But looking at the early technologies, which depended on the printing industry, I'd say that Richard Feynman wasn't the one who invented the concept of nanoscience. If we go back in time and think about Gutenberg and his printing press, Gutenberg really laid the foundation of microlithography in the 1400s. when he was able to reproducibly make patterns on the scale of a few micrometers, do it cheaply and reproducibly. So that's really what lithography is a kind of printing technology. And so what generally it involves is taking a thin layer of a patternable material, a radiation-sensitive material, exposing it directly, which I think is the future, or more conventionally through a mask at a particular wavelength. And then after a thermal treatment, inducing solubility change that can be revealed in a development process, and then ultimately some processing step takes place after that, perhaps etching, perhaps something else, and with multiple steps we can build up a microprocessor or a memory chip, or build a complicated small-scale device. If the material disappears in the exposed area, it is a positive resist, and if it stays behind where it's been exposed, it's a negative resist. And so this kind of terminology again comes from the printing industry and the photographic industry. So anybody can build a photoresist, but to make one that is suitable for semiconductor processing, you need an exposure time, a bake time, a development time in the matter of seconds. You don't want to have a product sitting on a rack for a long period of time for a process step to finish up. And so that's a piece of it. And the other part is it has to be essentially perfect every single time. I like to think if we had the perfection of lithography in the pharmaceutical industry or in the chemical industry, we'd be able to afford so many different medicines, perhaps, because they were made cheaply and reproducibly, and we wouldn't have to worry about some of the purification details that are necessary. So if we want to change the solubility of a resist, basically, and this is even today's inorganic systems used in extreme ultraviolet lithography, you basically have these three choices. One is cross-linking, next one is chain scission, and the third is a polarity change. Now, typically a resist is a polymer, so a high molecular weight macromolecule. If you take a macromolecule and stitch it together through cross-linking into a network, the solubility is reduced. A big molecule is less soluble than a smaller molecule. And so this is a method for producing a negative tone image. On the other hand, if you could take a polymer chain and break it into smaller components, maybe its original building blocks, that improves the solubility, or in some cases makes it so volatile that it evaporates. And that's a method for making a positive tone resist. Now, each of these has challenges. So if you take a negative tone system, it may still swell from a particular solvent if you're trying to develop it. And so that can lead to imperfections. If you have a system that breaks into small pieces and it's volatile, in some of the vacuum systems and high energy radiation that's used, it could lead to deposition. So none of these systems are perfect. In addition, there was concern, and I'll say more about this shortly, the concern in the 80s that there wasn't going to be enough radiation from a particular light source. And so there was a need to develop an alternative approach that enhanced or magnified the work of a single photon. And this particular process, now known as chemical amplification, leads to a polarity change in the resists. You can see the red dots on a chain being transformed on exposure to radiation to white dots. And what this represents in a cartoonish form is a chemical deprotection caused by a photoacid catalyst that's generated in the area of exposure. And you go from oil-soluble polymer to a polymer that's soluble in aqueous base, and this remarkable solubility change actually enhances your ability to make very small patterns. So the combination of chemistry and physics is a very powerful asset, and it's used to make the tiniest of patterns. And even today, almost 45 years later, after the invention of chemical amplification, we still depend on that, although there are new methods being developed, some of which I'll tell you about. This particular slide is, to me, a very interesting historical document, because again, it shows the expected progression on the ITRS roadmap to go from 280 to 150 nanometer, to go from 365 nanometer radiation to 248 nanometer radiation to 193 nanometer radiation. And then around the year 2000, it was thought that 157 nanometer lithography would step in for a short period of time, provide a technology gap fill, and then it would either be scalpel projection, e-beam lithography, or extreme ultraviolet lithography. Nobody knew for sure at that time. And history went in a somewhat different path. 193 nanometer immersion was added to enhance the capabilities of 193 by putting a drop of liquid between the resist and the lens. You can change the optics just enough to improve performance. And then, and so this happened around the year 2000. And then it was unknown at that time who was going to win. So I can tell you today, EUV has won. And we're going to talk about the path from the early days of 365 and 248 to today's EUV in the rest of this seminar. All right, so a photoresist is a very critical photosensitive material whose job is to transfer a pattern into a substrate. But it has to do a lot of things. It has to stick to a substrate. It has to undergo a radiation-induced solubility change. It has to have etch resistance. A photoresist has to resist something, and it's through the etch resistance. It has to be developable, preferably in aqueous base. It can be in other solvents, but water as a developer is preferred. And basically, you want it just to vanish when it's not wanted. So it's one of those, it's an incredibly important material that absolutely does not appear in the final device. In the end, it all has to go away. Now this is a nice slide. I borrowed it from Grant Wilson, who was one of the inventors of chemical amplification, and it just talks about the relative scale of things. So if you think that a single chip might be as big as North America, it on it a freeway is a 40 nanometer line. This slide comes from some decades ago. So a defect today was a car 4 meters wide. In 2006, the defect is a pothole. At the moment, defects today are the size of a volleyball, and eventually we want to have a defect the size of a baseball or no defects. And so these are the relative scales. So imagine you're in a satellite looking down at North America. Those defects can be critical, but they are tiny, and they're through improved improvement in performance, they're slowly being squeezed out of production semiconductor devices. Now, one of the things that the person inventing a new photoresist has to fight is how do you achieve the resolution that's necessary for a particular technology node. The photoresists have a reasonably large molecular weight that keeps getting smaller and smaller. They have a molecular weight distribution, so photoresists are not perfect molecules. They're collections of different composition and different size molecules. And that is changing today, but that is an area that's not been implemented. So that's part of the future. Photoresists can swell. They might have residual stress. This picture I have here shows a photoresist that has a high aspect ratio that's been pulled off silicon wafer simply through the forces of development. And you also have the problem that it may be imperfect. And so it is you have to worry about so-called line width or line edge roughness. And so you have sensitivity, line width roughness, contrast, all of these different factors you're trying to balance. All right, so what I'd like to do over the 2 days, two sessions, is talk about high resolution deep UV lithography without chemical amplification, 193 nanometer immersion, 157 lithography, e-beam lithography, and self-assembly. And then talk briefly about EUV lithography and just touch on some of these topics I'll reinforce later in the next session. So part one, or this is what the recorded talk will be. Part two will be live a little bit later. But let me go back in time. This is the history of lithography. It all started was all started by this interesting gentleman, Nicephore Niepce, who invented lithography, or maybe micro lithography. What he did was he invented the first photograph. And this is a picture. It was printed with bitumen of Judea in the early 1800s. You can see he set up his camera. It looks like a parapet or a rooftop. And that was the quality of the image. But it's fantastic. So where light hit, there was a chemical transformation. And where light didn't hit, we see the dark features. And so, again, lithography. Now, that is not very uniform. It's not able to transfer, really form a pattern that you can etch. That work came somewhat later. And this is the work of William Talbot. And what he found was that protein with a particular chromium oxide had high sensitivity, had poor shelf life. We wouldn't imagine using it today. But in fact, this process, if you remember the cathode ray tube, this particular process was used to make electron gun masks, even through the total life cycle of manufacturing CRT tubes. So this process developed decades ago, centuries ago, had a very long use life. Now, things started to turn into closer to what we consider modern lithography in the work of Louis Minsk, who was at Eastman Kodak at the time. And what he did was he looked at cinnamic acid, connected it to a polymer, used the photodimerization of the cinnamate group that led to cross-linking. And so he developed this very sophisticated, very reproducible negative tone photoresist. And so this was used not for photography, it was used in the printing plate industry. And again, so that's where the terminology of photography in the printing industry has entered into into photoresist. And in fact, these types of compositions used for the printing industry were ported directly into the early manufacture of some of the earliest integrated circuits. Okay, so moving forward, what I'd like to do now is march through current photoresists, current strategies, and we'll take you forward until we have time for a break. The first thing I'd like to talk about are resists without chemical amplification. Now, it seems a funny way to design them because chemical amplification was developed decades later than these photoresists, but at the same time, chemically amplified photoresists are so important, so ubiquitous in the industry. Everything else is defined in terms of their capabilities. So use this as a roadmap, and I will start talking about some of these resists that are known to people doing direct write e-beam lithography because they still function very well. All right, so resists without chemical amplification are an established technology. They're mostly used as e-beam resists. They were used as the original basis of deep UV resists, but lots of progress has gone on since then. They can be very high resolution, and one of the interesting ironies of chemical amplification is it requires an acid catalyst. That acid can diffuse, and if you're not careful, it limits the resolution. So resists without chemical amplification can have higher feature sizes, and sub 30 nanometer, even sub 10 nanometer features are possible. But the reason chemical amplification has been so useful is that most of these non-chemically amplified resists are low sensitivity. And so one of the things that has driven research and development in this area is how to solve these kinds of sensitivities. All right, so I think most of the folks in the seminar know electron beam lithography. These are some of the most beautifully sophisticated but elaborate and expensive systems. They are often characterized by long write times. And it's this kind of system that most academics or research facilities use because sadly, we have, if we have grad students or postdocs, we have time to burn a relatively low cost. E-beam systems are not used as much in manufacturing unless you have something very specific and something very special to make, and you need it now rather than waiting for some major process or a development to take place. The simplest resist, again, one that we would use in academia, is polymethyl methacrylate. And what happens is when the electron beam hits the resist, it can be induced through bond breakage to go into a high energy intermediate state. And this particular polymer has a fairly long-lived intermediate state. And so that enables, instead of simply cross-linking, enables depolymerization to occur. And so it is a low sensitivity system. So 800 microcoulombs per centimeter squared is a typical sensitivity, which means it's not very sensitive, but it can give excellent resolution. And with a superior system, it's possible to get certainly below 30 nanometers. PMMA itself, as I note, is not very sensitive. A sensitive system in e-beam units would be 10 microcoulombs per centimeter squared, roughly. So 800 is much less sensitive. And so people have developed variations of PMMA. What they're doing is they're tuning the stability of the radical and giving the unzipping reaction more time to occur. So this table shows some of the compositions you might find for much higher sensitivity PMMA analogs. And so anywhere from 40 down to 12 microcoulombs per centimeter squared. A polymer such as polystyrene, so those were positive tone resist because they unzip, the polymer disappears. Also fairly reasonable negative tone e-beam resists are based on polystyrene. You can cause cross-linking, but you can enhance the change in solubility of the material by tinkering with the structure. Something that forms a much more high sensitivity negative tone resist is this polyvinyl benzyl chloride. So if you add that as a moiety, it'll tend to go negative. If you have a PMMA type backbone, it'll tend to go positive. One of the interesting things is the sensitivity of these different polymers. And it turns out if you're trying to cross-link a material, you want to have a higher molecular weight. So molecular weight is something that you can build into a higher or lower molecular weight you can build into a photoresist system, and you can use that to tune the performance. This particular table, the way I look at it is that if you want to make something insoluble, you want to build up the molecular weight as close as you can to infinity. And so something that has a 300,000 molecular weight versus a 22,000 molecular weight, if it has a higher molecular weight, it's closer to infinity in a very simple-minded way of thinking about resists. You can also look at other chain scission systems and improve the sensitivity compared to PMMA. As I noted, you can put a phenone type of group onto that. It's more easy to cleave. This is PMMA, phenyl isopropyl ketone unit, and so that is sensitive to radiation. And you can also use a chloroacrylate in addition to alpha methylstyrene. This is the so-called ZEP composition. It's much faster, and again, it's known to give very high resolution. So higher sensitivity, higher resolution. What's not to like? Interestingly, jumping ahead a little bit, ZEP resists are known, but they have not been explored for extreme ultraviolet lithography, which suggests to me that although electrons are involved in e-beam and chain breakage is involved in, electrons are involved in UV lithography and chain breakage is involved. The mechanisms are not the same. And so it's tempting to say, just use an e-beam resist at extreme ultraviolet wavelengths. That's not proven to be the case. There are important and subtle differences. Okay, so in either case, both examples result in a more stable radical intermediate, and that leads then to better performance. IBM also patented many years ago a so-called terpolymer resist with a sensitivity below 10 microcoulombs. It's a positive tone resist, and it's very simple. It just takes maleic acid, dehydrates it to form an anhydride, and also has some content of methyl methacrylate. And so this system works very well, but making identical materials batch to batch is a challenge. Okay, so that is one type of scissionable resist. There's also the well-known polyalkylene sulfone, in this case polybutene sulfone, that is a very sensitive resist, but in terms of plasma etch, it's not good because this particular polymer melts like butter when exposed to the plasma. But it's an important suggestion about how you can improve the performance of a scissionable resist. It turns out SO2 and 1-butene are the monomers of the building blocks of this type of resist. And so you can polymerize it, make the polymer, and on exposure, it reverts back to the monomers, and these components can then evaporate. So it's an all-dry development system. And so people have reinvigorated these materials for extreme ultraviolet lithography with some success. These types of polymers were, as far as I know, first looked at Bell Labs as a mass writing resists. And again, they go in and out of fashion depending on what's available. They're somewhat difficult to make, and they also have some difficulty in handling. So there are other systems that are more popular, but they exist and they do work. And so this system with very poor etch resistance can be added as a sensitizer to a Novolac resist system, as it was done at Bell Labs, and then it makes a better patterning system. You can also overcome poor etch resistance in these types of systems by incorporating silicon. And so silicon has been used in so-called HSQ resist materials. The batch-to-batch variability is fairly high. Reproducibility can be good or bad depending on circumstance. Moisture is potentially a problem. And yet for really very, very high resolution, so very tiny dimension features, in an academic setting, you would use something like HSQ. And this particular polymer also can make a negative tone system through cross-linking of these double bonds and counting on the silicon to have good etch resistance. So they also work. And Bell Labs, again, was a source of lots of interesting resist technology some decades ago. And so this epoxy-containing methacrylate system, because of the cross-linking associated with the epoxy, works well. So it's radiation-induced ring opening and cross-linking that can occur. Finally, epoxy resists have been looked at as molecular glass systems. This, in fact, is a ring compound with an epoxy group, and that has been used as a negative tone, good etch resistant system. And you can see other variations in these materials. Okay, so key concepts to keep in mind for these types of materials are to improve sensitivity of a scissionable resist. You build in bonds capable of cleavage. You ensure stability of the intermediate so it has time to depolymerize or fall apart. And you can also consider release of neutral species. So once it's loose, it's going to disappear, and you're not going to reform a polymer or lead to additional cross-linking. So scissionable systems are all positive tone, and so they exist, and they're seeing a resurgence thanks to the studies in extreme ultraviolet lithography. However, as wonderful as e-beam lithography is, and I spent, and my group has spent a large part of their existence working on it, only optical lithography can provide the information output you need to mass produce all these semiconductor devices. And so that's where most of the energy, most of the advances have been made in the last few years. So I've jumped forward on the scissionable systems. Let me go back in time and talk about Resist, because they were the first resist system really invented with a large focus on the semiconductor industry. At that time, the feature sizes had to go down, and people were working very hard to go on to the next stage in device development, and so they needed something to perform better. And so this resist system, again, out of Kodak, because of its expertise in printing, newspaper printing, for example, printing plates, what it did was it took an isoprene polymer made synthetically, and with a little bit of acid, it cyclized the material. So rubber, is soft and squishy. By this acid treatment, it made it a harder material. You want that hardness in order to retain the patterns that you produce in it. You don't want it to flow. And using this interesting photomolecule, this bis azide, on exposure to UV, you knock off a couple of nitrogen molecules. You're left with this very reactive nitrogen that can go after the double bond and stitch it all together. So these are negative tone resist materials. And so the co-inventor of this material is shown here. And this was a huge step forward, both for lithography and for the semiconductor industry. And again, this chemical cartoon shows the nitrogen group going after the double bond on UV exposure and cross-linking the material. It worked well at around 360 nanometers. That's the maximum absorption of this particular photoactive compound. And so we were automatically going to the shorter UV wavelengths and driving down minimum feature size. And again, this sort of chemistry was very, very effective and worked well. And if you're interested in a reference for these types of systems, I really point you to Grant Wilson and Murray Bowden's monograph published by the American Chemical Society, which really talks about a lot of these older technologies. Okay, so we go from 360 down to 248. There was need to go to shorter wavelengths. And so at 248, one of the first new chemistries that came about used this interesting concept of a dissolution inhibitor. So it involved taking Novolac, which is one of the first synthetic polymers from the late 1800s, and blending it with diazonaphthoquinone. And what happens is the diazonaphthoquinone added to the Novolac makes it insoluble. It's a rather hydrophobic molecule. But on exposure to light, it undergoes a photochemical rearrangement, a Wolff rearrangement, as it's known. And it goes from being this hydrophobic material to one that after rearrangement has a carboxylic acid, and so it's easily soluble in aqueous space. And so in the exposed area, so hydrophobic, in the exposed area, a chemical change takes place, it becomes hydrophilic, and using water developer, you can wash it away. So important from a new concept point of view, but also important from more environmentally friendly processing. So these are the DNQ resists, where the Novolac itself is soluble in aqueous base, the combination is not, and the transformed material is even more soluble in aqueous base than the original Novolac. All right. Now, this was great, but if you look at this UV light output from a mercury arc lamp, what you see is we went from 360, 365 light down to 248. And as we tried to march to smaller and smaller dimensions, we were dealing with less and less light output. And so there was a tremendous concern that as we went from 248 to 193 to 157 to UV, there was simply going to be no light sources that were producing enough energy to carry out the chemistry that we need. And so this triggered, catalyzed some inventions that led to chemical amplification. So this particular molecule, known now as a photoacid generator, was explored at GE research labs by Jim Crivello as a proton source that would photo crosslink epoxy materials. And a team working at IBM Almaden, Hiroshi Ito, Grant Wilson, later joined by Jean Fréchet, who was a professor at the University of Ottawa in Canada at the time. What they did was they took this photoacid generator and combined it with polyhydroxystyrene that was protected by a tertiary butoxycarbonate group. And this is known as a protecting group in biological synthesis that is easily removed by acid catalysis. So what happens? We have the photoacid generator, it generates a proton. The proton goes after a carbonate group. It catalyzes release, CO2 is produced, isobutene is produced. These evaporate, and then a proton is produced. So one photon leads to acid, a proton, but this chain reaction keeps generating protons. And so one photon can generate thousands of chemical reactions, and suddenly you have chemical amplification. So that's where the name comes from. And if you if you heat this particular polymer, if you go high enough in temperature, this T-Bach group will pop off. But with acid catalysis, it will pop off at a much lower temperature. So if you bake this material around 125, 130, 140, 150 degrees C, you can deprotect in the acid-rich region, and you do nothing in the area where acid has not been generated. So this is fantastic. And suddenly the whole world turned to chemically amplified photoresists. And this is an example of a variation on the Wilson, Ito, Fréchet composition. It was just based on hydroxystyrene. Here we have a T-butyl ester that acts as the leaving group. But you see these fantastic high vertical features that are produced, just wonderful. And so this led to a revolution in photoresist design, in advances in the technology. So along with the photoresist, a whole series of non-ionic and ionic photoacid generators were produced. It turns out, while you don't see this in these figures, a lot of these materials are fluorosulfonic acids. And so this introduction of fluorine, and it's necessary in these systems in order to make a super strong sulfonic acid. This is chemical amplification has led to present day concerns about fluorine in the environment from the semiconductor industry. Again, PFAS, this is probably the last time I'm going to note that, but it is an issue that I think the semiconductor industry is dealing with in a good way. So again, I showed you before with the Novolac system, the D&Q Novolac, the dissolution rate differences were important in being able to create patterns. Well, this polymer is very slow to dissolve in aqueous base. After deprotection of the T-butyl group, freeing a carboxylic acid. This is much faster to dissolve. And so we have the solubility difference that can lead to a positive tone pattern. So additional things that are thrown in a photoresist are bases, surfactants, dissolution inhibitors, all of which are used to tune performance, improve shelf life, improve deposition, but the basic concepts stay the same for chemical amplification. Now, as the industry evolved, they needed to go to shorter wavelengths again. So they had chemical amplification in the quiver, but they had a problem. So all the original 248 chemically amplified resists are based on structures that had aromatic groups. Aromatic groups absorb at 193 nanometers, so you can't get light through the system. And so there was a tremendous amount of work to figure out how to make a 193 nanometer resist. And they found that methacrylate groups were transparent at that wavelength, and alicyclic groups were transparent at that wavelength. And you could get your etch resistance, the photoresist, resisting etching, through the use of these alicyclic groups. And once that was realized, people were off to the races. So this is the first poorly etch-resistant 193 nanometer resist, but it was based on methacrylic acid and T-butyl methacrylate. Great transparency, excellent solubility. So how do you fix the etch resistance? And you do that by putting in alicyclic structures. So this is one composition that was looked at. It's the so-called coma resist, but the presence of carboxylic acids, too many carboxylic acid leads to film swelling during development. And so you can think of it as a transitional structure. Other systems that were introduced include, well, fluorine is back. This hexafluoro isopropanol group found it was great, and it was less prone to swelling compared to carboxylic acid. So I don't know exactly what's in today's 193 nanometer resist, but probably some of this. And you can see other components. So once there's an idea established, resist development can move along incredibly fast. And so incorporation of lactone groups is also used today to increase solubility. So sesquioxanes can also be used as a 193 nanometer resist. And with silicon, you have fantastic etch resistance as long as you can get the solubility. And so these types of structures have also been looked at, but they're not as prevalent as the main chain materials. Okay, so around 2000, question is where would we go next? And there was debate over whether it would be 157 nanometer resists would have their own peculiar features, or what we would do. But in the end, the immersion lithography won. And again, that's putting a drop of liquid, excuse me, between the lens and the photoresist. Typically, the liquid is water, and it changes the light path significantly. And so it gives you better depth of focus and enhances resolution. So immersion lithography is a simple fix to a complicated problem. And the industry really swiveled on a dime in order to implement this. So you didn't need to know new chemistry. What you had to do was develop the lithographic technology. And so that is what is used in most production today. And it's become very, very successful. Pardon me. So I do, since this is a historical retrospective, I do want to mention one other thing. So there was a short, a multi-year diversion to explore 157 nanometer lithography. And at that wavelength, you could have no aromatics, no real acids, because they absorbed at that wavelength. And so it turned out fluoropolymers and activated alcohols were used for base solubility. This shows a study where the absorptions of different chemical compositions was looked at at 157 nanometer wavelengths. And it turned out fluoropolymers were among the most transparent. And so, again, off to the races to try to develop systems that would provide next generation lithography resist for 157 imaging. And this shows you a particular composition of resist that, as somebody in the industry told me, was for about a 4-week period, the world's best 157 nanometer resist. It came from my group. And at the end of that, the industry said, wow, we can't figure out how to solve the optics problem for 157 nanometer lithography. We're going to walk away from this whole thing that we've just spent all this time in. And so they did. And so this particular resist is a fantastic historical artifact. Again, for a month, it was the world's best 157 resist until nobody cared that there should be a 157 nanometer resist. But we managed to pattern it. It was really rather good. And so often in this area, there are technical successes, but business failures. And that was the end of 157 nanometer lithography about the year 2000. Okay. Incredibly tiny features. Really want to be able to go down to the 5 nanometer range. And so these lines that are around 10, possibly 10 nanometers involve just a few polymer chains. Bunch of really interesting problems to sort out. All right, so that's an example of a technology that lived for a brief time, was a technical success, but a business failure and not useful for anyone except historical artifact. I want to close with a brief discussion of self-assembly as an alternative method of patterning. So I'm racing through, I'm saying that, all the best features are made using photon-based lithography, but there is another interesting area that takes advantage of the ability of polymers to self-assemble. And so what this involves is the use of a blockopolymer, so a polymer made of 2 different types of components. It turns out the thermodynamics of mixing of polymers is very poor, and so these components want to phase separate, but they're trapped to live together. And as they phase separate, they form a common interface. And if you design them right, for example, you can make layered systems that phase separate, or you can make cylinders that phase separate. So you can imagine if you could take a block of polymer, process it in a way that these cylinders stand up, and then remove one of those components that makes the cylinder, you have an alternative method of patterning. And so for the last, I guess I would say 15 years, this has been a hot topic. At one time, it was going to be the future of lithography. Then it became dead, and now it has come back to life. And I'll tell you very, very briefly about that, and we'll wrap up our first session. The important thing is, because these are molecular, you can design them to have different feature sizes. And so you can produce 10 to 20 nanometer structures. You can produce 5 nanometer structures that form spontaneously. So this shows some early work using styrene butadiene and styrene isoprene, where a device was actually built using blockopolymer patterning. The blockopolymer was laid down. The reactive ion etching was used to eat up the softer part of the photoresist and leave the harder part of this blockopolymer photoresist behind. And then through reactive ion etching into silicon nitride. Pillars were made. And so an odd quantum dot memory array was built. So you can make holes, you can make dots, you can build a structure. This shows early work where all they were doing was reproducing the block copolymer patterning. But now the understanding of phase separation and the ability to direct assembly has improved so much. You can make very precise structures. So this is a nanocrystal flash memory transistor that was built by researchers at IBM in the early 2000s. Chuck Black is now working at Brookhaven National Lab, still in nanoscience, and I understand Catherine Guarini is an executive in the semiconductor industry. But here you see a structure that was built without conventional lithography. It wasn't direct write. It wasn't optical lithography, optical projection lithography through a mask. It was self-assembly, so a true device for that. You can look at other interesting structures that have been built, include silicon for phase contrast. You can also incorporate components that you saw earlier in the fast e-beam resist or in the early chemically amplified resist and do other things with that. So these guys are self-assembly. They don't interact with light. These could be made to be both patternable by light as well as have self-assembly. And you can change the kind of pattern through different types of processing. So this involves solvent annealing, where you can make a so-called fingerprint pattern, lines and spaces, and alternatively, by processing it differently, the same resist, you can make a series of dots, and you can go back and forth between them. So these were all things that were a dream in the early 2000s. But what eventually was discovered that you have methods that you can use to guide the assembly. So I think you can see here the lines parallel in this lying parallel in a trench, and you can also see the lines forming a bullseye. We're directing the assembly of these phase-separated structures. And so today, what people are thinking is that you can use conventional lithography without pushing its limits to create guideposts. You can lay down the block copolymer on the guideposts. It self-organizes directed by the guideposts, and then you can make much smaller lines and spaces without the need for these very costly, very expensive EUV systems. So it's time-consuming, but with a very well-controlled process, you can make advances in devices. And people are working, for example, my good friend and collaborator, Paul Neely at the University of Chicago, is working on block copolymers that have very sophisticated molecular designs, very precise control of surface chemistry. And so you can drive the assembly much, much better than what we can today. And people now are building advanced chips using directed assembly, small scale structures, and they're doing it successfully. So it's gone beyond demonstrations, and some companies are considering using directed self-assembly, DSA, as one of the process steps in their patterning quiver. All right, I think with that, I'm done with the first part of my presentation. I'll be coming online soon to answer questions for you, and I'll be then picking up with a second part of my presentation. Hope it's been interesting so far. Certainly lithography is pretty amazing considering all the options and the different directions that are possible today. And again, I'm delighted to take part and looking forward forward to meeting you all in person in a short bit. Take care.
As the chair of the third Direct Write Lithography workshop and webinar series, I'm excited to introduce Professor Christopher Ober, a leading figure in material science and engineering. Professor Ober, the Francis Nowot Bard Professor of Materials Engineering at Cornell University, has made major contributions to polymer science, nanofabrication, and lithographic technology, and we are thrilled to have him with us today. Professor Ober's academic path includes a BSc from the University of Waterloo and MS and PhD degrees from the University of Massachusetts. At Cornell, he's held key roles including Interim Dean of Engineering and Director of the Department of Materials Science and Engineering. He also led the Cornell Nanoscale Science and Technology Facility until 2023 and is now a Program Director for the Polymers Program at the National Science Foundation. Throughout his career, Professor Ober has guided over 50 PhD students, worked with more than 50 postdocs, published 600 plus articles, and holds over 40 patents. He was recently elected to the National Academy of Engineering in 2023 and the Canadian Academy of Engineering in 2024, and is a fellow of several scientific societies, including the American Physical Society and the American Chemical Society. Today, he will present he did already half of it, the history of lithography resists, offering a deep look at how lithography resists have evolved and where the future is headed. So thank you again. Thank you very much, Christopher, for offering to do this webinar.
Let me see if I can get screen sharing and then see if I can share the same thing, not the one that was just presented. Okay. Let's see. All right, well, you'll know this is live because I'm going to start at the end, I think.
We can see your screen.
Yeah, the question is, I'm seeing something different than you, so let me get rid of the other one. Let me go here, let me scroll to this. And I think, all right, I'm going to get rid of all the questions and shrink that down so I can actually see what's going on. Okay, I see your lovely face, Michael. You're on my screen here. Okay, so I want to switch to part two. I apologize for breaking it up this way. There's a lot to say, and I thought it would be an opportunity to give to have a break in any case. And I've also grown a little bit suspicious of the stability of Zoom. Generally have good luck, but at least you've heard something guaranteed with the recording. Okay. All right. And again, I want to acknowledge all the people that have supported the work and also my group members. So let's jump in. So this is a brief summary of the previous presentation. It's pretty clear that we continue to advance the ability to make nanoscale structures. We're again seeing an explosion of new methods and new materials brought on by the search for smaller and smaller feature size. Right now, we're shifting to exploring extreme ultraviolet lithography. And so that brings up a whole host of new molecular designs and new chemistries. And we're in a situation with EUV where it really does rival the best of E-beam imaging. There are other methods, self-assembly I talked about, step and flash, a kind of micro-contact printing. I've not talked about that, but that perhaps is a viable alternative. And the great thing about this is, I don't know how many of you are focused on semiconductors, but one of the great things the semiconductor industry has done is made these techniques available for all kinds of technologies. So work in medicine, quantum science, which is not classical semiconductor, electronics, all that is possible thanks to this massive investment in making computer chips. Okay, so what I want to do is talk briefly about the problem of photolithography under extreme ultraviolet wavelength. I'm going to talk about molecular glasses, what I call nanoparticle resists, which are really metal organic clusters, the way we practice them today, scissionable resist, and talk about perhaps what's next, with the understanding that as we go to smaller and smaller feature size, we really need to make things with molecular precision, because what used to be forgivable as a molecular inconsistency when we were trying to make things that were micrometer in size using perhaps 248 nanometer radiation, is that those kind of imperfections are no longer acceptable as we try to produce these tiniest near molecular feature sizes. Okay, so what's extreme ultraviolet? I don't know how many of you have used it. I don't know how many people encounter it. But it's not really ultraviolet. It's soft X-ray. The name is a strategic one, and it was caused by the fact that several companies 30 years ago were investing in X-ray lithography, and it basically was a failure. What they realized, what management realized, was it was incredibly expensive, incredibly unreliable. They could only make a few hundreds of a device, and then they had to replace the masks. It was an enormous problem, and management told lithographers, don't ever come and talk to us again about X-ray lithography. And yet the lithographers knew they needed to go to these shorter wavelengths. And so they thought about it for a while and said, management knows that UV lithography is good. What if we just change the name and use UV lithography in it? And somebody said, we know, we'll call it extreme ultraviolet lithography. And so that's the name we're dealing with, even though it's very unscientific. It represents soft X-ray at a 13 nanometer wavelength, and it has all kinds of problems that come with it. And there's been just unbelievable technical innovation that's gone forward to make this possible. So this is a schematic of a EUV stepper. And the first thing that had to be done was a big improvement in lasers needed to be worked through. So companies like Intel bought a Cymer laser company and basically said, you're going to be working on solving this EUV problem. Then people developed a technique for building, for basically introduce a stream of molten tin droplets that were synchronized with a laser, so that the laser pulsed on the droplet as it was dropping by. EUV radiation is generated at that point continuously. And then all of this has to be in vacuum because, as somebody said, everything absorbs EUV radiation, so that includes air. And so once the EUV is produced, because the lenses would absorb EUV radiation, it has to be all reflective optics. And eventually, after bouncing it around, the light being reflected off, effectively a mask on a surface, and then it is focused on the wafer. After all of that, you have almost no light getting through. So the resists ultimately have to be very sensitive because most of the radiation is thrown away with this sub 100% reflectivity. It's just an amazing problem to build the stepper, and it's an amazing problem to build the photoresist system. Hey, so with all these challenges, what do you do? And so this is a fantastic periodic table. I believe it comes from Robert Brainerd at the State University of New York, Albany. And what it does is it lists radioactive, toxic, and expensive elements, as well as the UV optical density for materials with a different element. UV radiation is different than UV radiation because we're no longer dealing with absorption by functional groups that organic chemists are familiar with, but in fact, it is an elemental or an atomic composition that determines whether light gets through or not. And so you want the radiation to interact with the element. So blue and purple is good. Everything else not so good. And you'll notice that the elements we use to build resist today, hydrogen, carbon, oxygen, maybe nitrogen, fluorine, they're low absorbing elements. And so you really need to be further into the periodic table, but you don't want to be radioactive. You don't want them to be too expensive, and you don't want them to be toxic. So with the whole periodic table to choose from, you'd say, oh, it should be easy. But in fact, it narrows it down. And so notice tin is purple, indium is purple. It still surprises me there aren't too many indium-based UV systems, and perhaps someday they will materialize. Okay, so that's part of the problem. How do you get the absorbance right? But stochastics is a term that the lithographers throw at the chemists and say the reason the resist doesn't work is because of bad stochastics. Now, what does that mean? What that means is, as I mentioned before, you have to have real molecular homogeneity at dimensions that really people haven't done a very good job of achieving that kind of molecular uniformity. Polymers that are often used in photoresists are very chemically heterogeneous. They have different molecular sizes. Polymers have different composition. They tend to organize themselves not on a lattice, but on a random arrangement. And so the lithographers have a point that how do you ensure chemical homogeneity? And so this will be a theme that kind of runs through what I talk about right now. Now, although these are all experimental systems, I think it's important to be familiar with these for a couple of reasons. One is that some of these systems are going to win and they're going to become available. The other reason is that although extreme ultraviolet is different, the mechanism is different than E-beam lithography, there are so many similarities. I think some of these new resist systems will be really, really useful for making the highest resolution E-beam features. So if that's something that you do or you want to do, watch this space, pay attention to the materials that come out here. Okay, so I first want to talk about molecular glasses. And this addresses one of the questions. Do you want big or do you want small structures? And I'm a proponent of small. So here's a typical hydroxystyrene polymer. It's arranged in a random walk. Its size is about 5 nanometers. It has about 50 of these units in it. And if you try to build a structure that's maybe 10 nanometers in size, and you think of this like a printed page made out of dots, you realize that these dots, these pixels, are pretty big compared to what you want to do. But there are other ways of achieving patternable molecules that are smaller in size, such as these molecular glasses, that might enable you to make a finer feature pattern. So they're smaller than a polymer. They behave a lot like a polymer. They have faster development. They have lower line width roughness. You can make molecular blends. You can do all kinds of things with them. They're not perfect, but they're an example of a step towards a superior system. Again, this is work for my own group, but there are lots of people playing in the space some time back. And these are examples of early extreme ultraviolet resists, where we were making optical patterns down to, let's say, 25 nanometers. All kinds of materials could be made successfully. Some were positive tone, some were negative tone, some were chemically amplified, some were not. And just for the public, I always like to point out that 30 nanometers is less than 1,000th the size of a human hair. So that's really small. Another advantage of molecular glasses is you can vapor deposit them. And so this is an example of a molecular glass molecule that was deposited using a PVD system and patterned using E-beam. So nevertheless, research stopped in this space. Industry moved on to other things. And for EUV, one of the things they moved on to were inorganic nanoparticle photoresists. Now, coming from the molecular glass size, to me, these are basically inorganic molecular glasses. And we stumbled on this particular approach because we've been asked by the semiconductor industry to make a new kind of immersion liquid. Remember the liquid that goes between the resist and the lens? And they said, can you make nanoparticles and load it into a hydrocarbon solvent? Because we may need a high refractive index immersion liquid. And this was yet another example of we did everything the industry asked for. And they said, thank you so much. You did everything we asked for. We're not going to use your technology. We decided to stick with water. But here's a couple of years of research funding. Knock yourself out and have fun. So what we did was we took the nanoparticles that we built for making this high refractive index immersion liquid and said, maybe we can make a photoresist out of it, a molecular glass. And so we did. And at the time, we thought 2 to 3 nanometer in size was small. It turns out it's not for these purposes. And we looked at the capping groups we put on these nanoparticles. And what we found was that by incorporation of a photoacid generator or a photoradical generator, we could make a negative tone resist. And in fact, these are much more complicated than that, though, because we can also make a positive tone system depending on how we develop them. So still things to understand about these materials. But an important event occurred when we demonstrated that with these nanoparticles, we could make, with EUV exposures, a screaming fast photoresist. This is a really fast resist for EUV. And we were able to get things down in the 25 nanometer regime, which had never been done before with these types of materials at such low exposure doses. And so this really reopened interest in advancing these types of photoresist. Okay, so we looked at hafnium oxide and zirconium oxide. They're poorly absorbing at EUV wavelengths, but remember we originally looked at them as high refractive index components of an immersion liquid, not a bad repurposing of some interesting technology. And we also were able to demonstrate that we can make patterns with all kinds of oxides. This is with ultraviolet 248 nanometer exposures. It turns out at EUV wavelengths, these are much, much faster systems. And then I had a brilliant postdoc join my group who said, you know, your particles look like the apex points of metal organic framework compounds. And they have the same infrared absorption spectrum. We can use the chemistry, vast libraries of chemistries to make much more pure materials. And that was an aha moment because we were able to address the stochastics issue by not making particles with different sizes, some average size, but by making molecules with precise molecular composition and ensuring everything was the same. And so by golly, we went from these white powders to molecular objects that could crystallize. So this is a pure crystal of this molecule. The solubility went up, and so we could get much higher loading of these oxide particles, these oxide molecules in a photoresist solvent. And we also had, again, near molecular perfection. So everything changed at this point. We went from these kinds of structures that have multiple molecular objects to something that's pure. And we then began to realize the reason these could be patterned was through a very complicated patterning mechanism where these capping groups, these ligands, sit on the nanoparticle, and our photoactive compounds carry out a ligand exchange to make them less soluble. And the EUV exposure also knocks off some of the ligands, and so we have condensation that also makes it less soluble. So we have a double mechanism for producing negative tone patterns. And in fact, this is some drawings from a paper by Bill Hinsberg, formerly of IBM, one of the experts in the development of chemically amplified resists, who recognized that all of these nanoparticle, these metal organic cluster resists operate under similar negative tone condensation mechanisms. And once we started to look at metal organic framework type of chemistry, we realized we could look at zinc and zirconium and chromium, indium. We could go through the periodic table of these materials. And so as a demonstration, we looked at zinc, and we found it's just a fantastic resist system that will never be in manufacturing because people don't like to put zinc on their device. But in terms of being able to pattern a material, you can really do things. And so these types of figures show that indeed with the zinc cluster, we could do the same thing we did with the zirconium, make very, very pure systems that behave well. And so we suddenly we became able to make 12 nanometer half pitch features with these kinds of systems. So this is one approach that we've explored, using metal organic cluster molecular glasses to get high performance in EUV lithography. But there are other ways. These metal organic clusters are by no means perfect. Maybe another way to solve the problem is to work on scissionable resists, which I mentioned in the first part of this presentation. The industry is aware of them. They've been using them historically for mask making technique, but never as a mainline photoresist for semiconductor processing. But work has gone on with them. And if you know about funding of research in the United States, you might have heard of DARPA. And DARPA was interested in the ability to make transient sensors. And so what they wanted was a polymer system that was a major component of a sensor that could be scattered in a field, perhaps to following an environmental disaster. Then these sensors could be optical, they could be acoustic, they could be chemical, and at the end of their use, they could be made to vanish. So this is a sensor with its device, perhaps an energy source, and so on. It was a very interesting exercise. But the key thing from photolithography is that they wanted plastic components that could vanish when exposed to heat or light for extended periods. And so that's where interesting work has gone on in these scissionable resists. And so from that work, we became aware of new polyethylaldehyde systems. In this case, we put a bromine on this particular molecule, and it completely changes the character of the polymer chains. We can have linear polymers, we can have cyclic polymers. The advantage of this, it has no end groups. Here we have to cap the polymer chain to make sure it doesn't depolymerize. And indeed, by 248 nanometer lithography with a non-ionic photoacid generator forms a nice pattern. We can use it with E-beam exposures. But with extreme ultraviolet exposure, it turns out the polymer itself is pretty stable. That's what this series of infrared spectra at different exposure doses tell us. And we looked with our colleague Greg Denbo at SUNY Poly on outgassing experiments and found out that basically without PAG, again, the polymer is stable. With PAG, it depolymerizes. It goes back to its original building blocks. Interestingly enough, and this is a key contrast between E-beam lithography and deep UV lithography versus extreme ultraviolet lithography. We can combine this polymer with a photoacid generator that will pattern at both E-beam and deep UV, and this resist is completely dead. But if we choose a structurally different photoacid generator, we can make incredibly fast EUV resists. So this is an exposure dose of less than 10 millijoules per centimeter squared, so really fast. And so I like to put up this, this chart and ask people, what's the difference between these different non-ionic photoacid generators? But it turns out that if you have a sulfur oxygen carbon bridge, this is dead at UV wavelengths. But if you have a nitrogen oxygen sulfur bridge, it's extremely active. And so my conclusion is the photochemistry under EUV wavelengths is different than other patterning methods, and we still don't completely understand that. Nevertheless, empirically, we can make advances, and we've been able to show that these kinds of materials are really fast and successful photoresists. And so we're working with a photoresist company right now to push these kinds of scissionable resists forward for EUV patterning. And I should mention that our partner in the metal organic cluster resists was JSR, and JSR bought a company called Inpria, and so they're the leading manufacturers of inorganic resists. Nevertheless, I'm always thinking about the next big thing, and I'd like to close with this. And so this is it's a bit of science fiction, but it's science fiction that may become science fact. So if you think about polymers, you think about photoresists, what you realize is that when we build a polymer, when people build a polymer, it's usually pretty imperfect. Most polymers are made of different building blocks. And when you build those building blocks, you can assemble them in different ways. And so in a pot where you've made a photoresist polymer, you might have one polymer chain that has 1, 2, 3, 4 different types of building blocks. You might have another chain a nanometer away that only has 2 building blocks. And there might be another chain, another nanometer away that has 3 building blocks in a different composition. It also has a different molecular size and has a different sequence. So it's no surprise the lithographers complain about the stochastics of polymers. But there are ways to make all the chains with the same composition, the same molecular size, and the same sequence. And my group and some others are working on that right now, and we're seeing important differences. So Lutz wrote or co-wrote a wonderful thought piece that inspired us some years ago. And he made the argument that in order to, that you couldn't use nature's machinery to build a controlled sequence polymer, because everybody knows polymers have to have a high molecular weight. But in fact, in photolithography, you don't need a high molecular weight, and you can use the machinery or borrow concepts from nature to build these very precise systems. And so there exist robot synthesizers that can build a polymer like that with a specific sequence. And working with friends at UC Berkeley, we're working on things called peptoids, not peptides, but peptoids, where we can build a very specific sequence using the so-called half monomer synthesis, where we build each repeat in 2 chemical steps. In a way, it doesn't matter whether it's a 1-step or 2-step. We have a robot, the robot does what we want, they build it, and then we have these materials to play with. And so one of the things we've been trying to figure out is if we can build anything we want, what should it be? And so we built things that have groups that look like the original chemically amplified resist. We have components that look like the etch-resistant components of 193 resist. We have chemical groups that are sitting there waiting for us to decide what we want to add. And so these are so-called clickable groups. And we're working on building ultra-low stochastic systems. And we found that if we take polymers of the same composition, the same molecular size, but a different sequence, oops, there we go again, we have different solubility characteristics. We can change the development behavior. So not only can we improve stochastics, but we now have the ability to absolutely tune solubility and resist response. This is a 3-dimensional plot showing different solubility envelopes for these 2 different materials. I'll tell you that having the resist components distributed uniformly makes a much better resist. And so just 18 months ago, we were building these kinds of systems, trying to understand what made a good resist. And very rapidly, we walked through different compositions, different sequences, and again, different solubilities. And about a year ago, we were doing e-beam lithography and beginning to see these small patterns with these strange bubbles, which it turned out was caused by our choice of a photoacid generator. And today, with a combination of a photoacid generator, we are able to produce, by EUV exposure, 24 nanometer structures. And more recently, we've demonstrated that in a PAG-free controlled sequence polymer, we're able to get down to 14 nanometer results. And we see no reason why we can't get even smaller. So I think this is the beginning of yet another type of photoresist system. Again, it will be ported over to e-beam and maybe deep UV lithography. And I'll just wrap up here and say that I cheated. It was supposed to be historical talk, but I'm also telling you a bit about the future. There's lots of space to play in this sandbox, and the good news systems are desperately needed. And so let me just stop here and thank you all for listening.
Thank you, Christopher. Thank you very much for this insightful presentation.